not going to talk about that. I think this book would be a good place to learn those from. So I'm giving a thumbs up to this textbook. Oh, geez, what happened? Okay, something happened to my iPad thing. What? Pardon me while I experience technical difficulties here. All right, I think I'm okay. Oh, it's not the 20th today. All right, confidence intervals. Let's talk about confidence intervals. I'm going to share my tablet here in a second. Um, so today I'm going to do a bunch of work. Oh, there we go. A bunch of work on my tablet as usual. But I'm also going to jump over to my document camera and show you something from the text for a couple times. And I'll also jump over to R a couple times, I think, because I'm going to talk about the ideas in my notes. And when we do some examples, I'm going to bring us to the text, and then I'm going to bring us to R to show us how we would do those examples in R. I'm going to focus on the concept of concept intervals, and I'm going to basically work and rework one of these examples that's in the textbook. So we're not going to get too far into section 1 of chapter 5, but I think I'm going to give you a good foundation on which you can understand it and exercise the understanding of confidence intervals. Okay, and if anytime you got a question about what I'm doing, I try to do my best to monitor chat, and I try to watch to see if people raise hands, but it's kind of hard. So I strongly encourage you to vocalize. Hey, Miller, I got a question. Or, hey, Miller, so-and-so's got a question in chat. Okay. All right, confidence intervals. Confidence. All right. So this is a topic in inferential statistics. And to remind you what inferential statistics is, to this point, we've been talking about descriptive statistics. You got a population, you calculate a mean. You've got a population, you calculate a standard deviation, or they have those parameters. They're given to you. Those are descriptive statistics. Inferential statistics is when you have a population. I'm going to call it omega, and you want to know something about some parameter, some measurement, theta, about the population. So what do? Well, we take a sample of the population and we do calculations of the parameter. And if we want to estimate the parameter, oftentimes the way we do that is we'll calculate an average value. Because the mean is an unbiased estimator, we know that if we calculate the mean of our parameter, then that's going to be approximately equal. Actually, we should say this. The mean of our sample mean is going to be the mean of our population. And this is a good way to understand what this parameter is. And so this means that oftentimes we're interested in how the sample mean varies as a distribution, but I'll come back to that. The idea is, and I'll just repeat, inferential statistics, we take a subset of our population and we make a measure from that sample, that subset, in the hopes to understand what the real parameter is. So we're inferring the population's parameter from our sample of the parameter. Okay, that's inferential statistics. So oftentimes when we have a measurement we're making, so a measurement of interest, and again, the book calls this a parameter, or could call it a parameter. We report it in the following way. And I'm going to use numbers here, like 25 plus or minus 0.5 millimeters if we're measuring a length, for example, or reporting a length. When you see a number reported in this way, remember this first number here is the sample mean of the measurements, and this 0.5 here is often the standard deviation, the sample standard deviation. And this number here, 25 plus or minus 5 or 0.5, you need to think about it on a number line. And what it means is your measurements are in this interval. Okay. And likely, let's do this in red because it's important. Likely, the population mean is in that interval. Okay, the real value you anticipate is in that interval. Okay. We're never really sure because we're only working for measurements, but we want to choose the width of this interval here to guarantee us, at least to the extent that anything in life is guaranteed, to guarantee us or assure us or give us confidence that the population mean is in that interval. Okay, everybody with me? These things are from samples. And what I'm going to talk about today is how do we choose this number here to assure us that the number we're trying to study is in this interval. So this topic is going to bring together a crap ton of stuff that we've studied so far. So it's going to be a real test for how you understand probability distribution functions, how they tell us about probabilities, maybe even cumulative probabilities. But I'll get to that. So I wrote down this. The idea is this. Because the sample mean is unbiased, for a population mean, i.e. that means the mean of our estimator is actually the mean of our population. People feel, so I was going to say we feel, but people feel comfortable exchanging X bar and mu freely and without warning. And this comes up in the conversations about confidence intervals. If you look at the popular press, when they talk about confidence intervals, they do not distinguish between the sample mean and the population mean. Okay, they will not. They're going freely and without warning between them. Okay. Let me add another phrase to this. People go back and forth between the sample mean and the population mean freely and without warning in casual conversation, in the popular press, in, around a lunch table or whatever. I'm here to remind you, this class is not a place for casual conversation about this topic. Okay. We need to be careful. So I'm going to try to be as careful as I can when we talk about this. And in fact, I'm going to start out a lot of what I talk about focusing just on mu, knowing that in real life, we don't know the mu of a population. and all we can get is the sample mean. But I'm going to talk as if we're gods and we're omniscient and we can figure out what mu is. Then at the very end of class, I'll switch to X bar. Okay. So if you ever have any questions about where I am, just don't hesitate to ask for that clarification, because this is not a place, this is not a day where we want to be casual about these distinctions. And if I'm confused about something, I will let you know and I'll follow up. So here's the big question, and I'm going to do this in blue. It's very reasonable to ask, how well does X bar approximate mu? Even though we know X bar is always going to be approximately mu, there's going to be error here, and we want to know how much error there's going to be. So that's what confidence intervals are going to address. How confident are we that X bar is close to mu? Okay. And you'll understand what I mean by close. That goes back to this idea of the interval. Okay. So today I'm going to relate intervals like this to a level of confidence. So to allow us to get to the point to understand that, what I'm going to do today is I'm going to talk about a random variable x, and we're going to suppose x is distributed normally with mean, mu, and variance sigma squared. And x is just going to represent some measurement. We don't care what it is. It's just going to be an abstract measurement. So today I'm going to repeatedly use the fact that the probability distribution function for a normal random variable is the bell curve. It's a symmetric curve, symmetric around the mean. And the inflection points, again, we remember that they occur one standard deviation away from the mean. And we are going to be looking at some value of x and asking questions about it. So in this case, x naught is a possible outcome. Okay, it could lie anywhere on the x-axis, because the sample space for the normal distribution is minus infinity to infinity. And the question that we're going to be interested in today to understand the mathematics of is, what is the probability that x gives us an outcome that's less than or equal to x naught? Okay. What's the probability? So given an outcome, what's the probability that we get another outcome from x that's smaller? In probability theory, we learned, I'm going to use green, that one interpretation of this probability is geometric. So we can look at the distribution and we can see that the probability is this area. The total probability under our probability distribution function is 1. The integral from minus infinity to infinity of our distribution is 1. So it's this area right here. It's the area under this curve here that equals this probability. So I'm going to do that in green. So this is the idea of, this is a central idea to understanding confidence intervals. So how do we calculate that area? There's two ways we can calculate it, three ways we can calculate it. So what is that? Three methods. Ugh. Legibility. Three methods to calculate. One method is to calculate this integral. And I gave you the closed form expression for the probability distribution function. I'm going to sneeze here in a second. For the normal distribution. Excuse me. And I told you this is really hard to calculate. But this is, in theory, you can calculate this. Another way is we can use a pre-calculated table. And I'll show you how to do that today. And the other way is we can use R. And specifically, we can use the p-norm function in R, and we would put x naught as the first argument. And then the second argument, we'd put the mean. And the third argument, we'd put the standard deviation. So those are three ways we can do it. I will never ask you to do it this way. I will want you to know how to do it this way. And I'm going to expect you to be able to do it in the third way. So I want you to know how we use tables. But I expect you to master using R to do these calculations. And I'll show you exactly how to do it. And what we'll do today is we'll go back and forth between the tables and R's, and we'll convince ourselves that they're giving us the same thing. Okay. So let me show you how we use a table. So what does the book call it? In the textbook, there's table A2. So if you got your textbook with you, now would be a good time to pull it out. Table A2 is called the cumulative normal distribution. And in parentheses, the authors say Z table. So if I were the author, I would have put a word here, standard normal. And what this is, it's the table that gives us the CDF values, the cumulative distribution function values for the Z distribution. And just so you recall, the Z distribution is the normal distribution with mean 1 and variance 1, or sorry, mean 0 and variance or standard deviation equal to 1. Okay, so somebody give me a number. Anybody have a favorite number that they want to?
42.
42? 42. Okay, so favorite number. Somebody else give me their favorite number.
7.
42, 7. And somebody else give me a favorite number. One more person.
9.
9. Okay, so I'm gonna say let's let well, let's see, what should this be? Let's let I want one of these to be my mean. So let's let 42 be my mean. Let's let 7 be my variance. No, let's let 9 be my variance since that's a perfect square. Okay. And what I want is I'm going to say 7 is going to be come on. 7, I'm going to take 42 plus 7 is 49. Okay. So let's ask the question this. I've got a random variable x that's distributed as a normal random variable with mean 42 and stand variation or variance 9. What's the probability that x gives me a value that's less than or equal to 49? So let's calculate that probability. And it's always good when you're learning this stuff to draw a picture. So we got 42 as our mean. I'm interested in 49 up here. And we've got our standard deviations that are 7 away. So my 49 is a little bit above. So my standard deviation is 3. So I've got 45 here and I've got 39 here. So I want to know the probability that I'm less than 49. So what's this area? So how would we do this in R? Well, let's look at this. We would type in P norm 49 because that's the value I'm interested in. And then we're going to put the normal random variables mean, which is 42, and its standard deviation, which is 3. So if you have your R open and available, now would be a time where you could just go and type that in and verify if it gives us the right number. I am going to do the same. I think. All right, I'm sharing my R window and let's clean up my console. I'm going to move around a window here. So I said P norm of 49 given my mean 42 and standard deviation 3. And I get 0.990187 or 847. So that means that there's a 99% probability that my random variable will give me a number that's less than or equal to 49. So what about, what's the probability that x is bigger than or equal to 49? Well, that's going to be 1 minus the probability that it's less than or equal to 49. And so I can just do the addition, or I can make R do it for me since there's lots of decimals. So R tells me that's 0.009815329. Okay, so there's a less than a 1% chance that I get a number from this random variable that's bigger than 49. Okay, thanks, Miller. That was real deep. Next. Well, no, this is why I wanted to tell you this. I know this is pretty trivial, but this number right here, I want you to see that it's this remaining complementary area. It's the area of this tail. I just want to point that out to you geometrically because this idea will come back to us. All right, so how do we use the table that's in the book? Well, the table in the book relates to the standard normal distribution. So to use the table in the book, I need to go from our distribution. Oh, here. I need to share with you my tablet. So to use the table in the book, I need to convert my random variable to the standard normal random variable. So what we're going to do is this. We're going to take our x naught, which is 49. Okay, so that's the value that I'm interested in. And I'm going to convert it to a z-score. So last time I told you how to calculate a z-score. You take the value you're interested in, and you subtract the mean, and you divide by the standard deviation. So in this case, it's 3. So 49 minus 42 is 7 divided by 3. So our z-score is 7/3. And that's approximately equal to 2.3 repeating.
Where did you get the 3?
That's the standard deviation.
Oh, okay.
The variance is 9, so the standard deviation is 3. Okay, so our z-score, I'm just going to rewrite that in here, is 2.333 repeating. I'll just put that up there. So we have the normal random variable with mean 0 and standard deviation 1, and we're going to ask, this is the question that the book can answer. What's the probability that a standard normal random variable will give us a number that's less than 2.3 repeating? So let me show you how to do that in the book. Okay. So I'm going to switch to my document camera. So you can see I've got my book here. And textbook, and I'm just opening to the inside cover. So it's a really easy table to find, table 8.2. And I know this is a little bit small. I'll zoom in here in a second. But I want to show you that even the table at the top has the pictures I was drawing. And it has a picture here. 0 is the mean, right? This is the mean of a standard normal distribution. And it puts in a z value here, and then draws the same vertical line that I drew, and then highlights the area to the left. So this table is giving us the blue area. The numbers in this table are the blue areas. And z here, you find z by looking here. So first you look down the column, the leftmost column, to find the number that's closest to the z value you want. And it continues over here. And you can see that these are increments of 0.1. And then if you go to the right, you can add one more decimal place. So you look up here at the top, you can see the hundredths place. So we're interested in what's the probability standard normal gives us a value less than 2.3 repeating. So if this z, well, I guess if this z were moved up to 2.33 repeating, and that's why this picture is different, because this page has z's that are bigger than 0. This page has z's that are less than 0. So if our z is 2.33 repeating, so it means I'm going to go down here to look for 2.3. There we go, 2.3. Then I want to go to 2.33. So it means I go over to this fourth column. And you can see there that value is 0.9901. So that's what I'm going to write down. But wait, Dr. Miller, this is the value, this is the z-score. This is the value of z that gives us an area of 2.33, not 2.33 repeating. And you're right. That's one of the weaknesses of a table of z-scores, or a z-table as our book likes to call it, is that it only gives us a certain degree of accuracy, which you shouldn't be surprised about. How can you improve your accuracy? Well, it's reasonable, and reasonable people will agree that you can interpolate. So the distance between this value and the next value up, looks like here it's like 3/1000ths. And our number, 2.3 repeating, is a third of the way between here and here. So you could maybe add a third of the difference, which is a 0.0001. So a reasonable person could say the z-score, or the z value for 2.33 or 2.3 repeating would be 0.9902. Okay, everybody with me? I'm just gonna report 0.9901. Okay. So let me go back to my tablet, which is gone to sleep. It thinks. Can you all see my tablet?
Yes.
Thanks, Patrick. So table 4 point, or sorry, table A2 tells us the probability of Z being less than or equal to 2.33 is 0.9901. Okay. Now, this was the Z-score for X naught. We can therefore say that the probability was this 47, 49. We can therefore conclude that the probability that our original random variable gives us a value that's less than 49 is also 0.9901. So this is the power of this table. This is why this table is so useful to people, or historically was useful, is that you can go back and forth between some standard normal value and the associated z-score of that, use the table to find a probability, and then that probability it translates to the probability that you're seeking. In the language of Calc 3, going from X to Z is a change of variables. That preserves area. And by preserving area, you're preserving probabilities. So the area under the z-score is going to be the area, or the area under the z curve is the same as the area under the x curve when you do the z-score transformation. And I'll do a couple more of these today too before we're done. But I wanted to show you how we use this textbook. All right. So I haven't gotten to confidence intervals yet, but let me get a step closer. So I'm going to be focusing on, or taking a different look, or different view toward example 5.1, the first example in chapter 5, section 1. And in that example, you basically have a random variable that has, it's distributed as a normal random variable with mean 12.05 and standard deviation 0.01. So let's use this random variable and calculate what's the probability that the random variable gives us something that this is right. Oh, yeah. Okay. So this is not what I wanted to ask. For what x naught is the probability that x is less than or equal to x naught equal to 0.075? That's what I want. So this is a very different question. In the previous example, we started with a value 49 and we wanted to calculate a probability. Now I'm switching it up. I'm starting with a probability, and now I want to find an x naught that has that probability. Geometrically, what that is this. I want to find an x naught here where the area to the left of it is 0.075. And I know my x naught is to the left of 12.05 because at 12.05, the area to the left of it is 0.5, right? This is the middle. This is the mean. This is the median. It's the distribution is symmetric. So if the total area under the curve is 1, then this is exactly half. So there's area is 1/2. My number here is less than 1/2, so I know my x naught is less than 12.05. Okay, so let's solve this equation. And that's what this is. This is an equation. Let's solve this equation. Yeah, so what we're going to do is this. The only way we know how to solve it right now is using the textbook. You could set up an integral here, but that's not going to help us because the integral is insoluble. You can't solve it analytically. We can only use the textbook. So the textbook is not for values of this distribution. It's values for the normal distribution. So I need to convert this x naught number into a z-score. So that's what I'm going to do. So x naught, what I need to do is I need to subtract mu and divide by my standard deviation. That's going to give me a z-score. So, and now notice I don't know what x naught is, but that's okay. So x naught, my mu is 12.05, and my standard deviation is 0.1. Right? Did I do that right? What did I say my standard deviation is? I want my standard deviation. Yeah, I want it to be this. So I want my mu. I want my variance. See, that's to be 0.1. Is that right? And then my standard deviation. Oh, man.
Isn't that switched?
I think that's switched. So, yeah, let's do it this way. So, if this is my variance, then my standard deviation is going to be 0.1. If you square that, you get 0.01. Okay, so down here, I need 0.01. Okay, so we proceed. So this tells me 0.1 times z naught is x naught minus 12.05. And I'm going to add all right, I need to stop. Oh. Yeah, I'm getting a little bit ahead of myself. X naught is going to be equal to 12.05 plus 0.1 z naught. Yeah, I got distracted. We're going to come back to this because this should look to you like almost, I mean, it should almost look like a confidence interval, or it should almost look like that interval we started out with at the beginning of class today. And it would look better if I knew what z naught was. And what I forgot is I don't have to do this to find z naught. I can just do this. So let me show you what I forgot. So remember I said that this linear or this change of variables from a normal to a standard normal doesn't change the area. So we can use this equation to find z naught using our table. Then we'll use the table to find the z-score we're interested in that corresponds to this probability. And then we'll know that the z-score of this is the same. And then we'll come plug that into here. The z-score goes right there. Okay, so let's use the table. So I'm going to switch us to the table. And the probability we're looking for is 0.075. So the numbers in the table are the probabilities. The headings and the column and the column headings and the row headings, those give us the scores. So we want to look in the table for 0.075. So there's 0.476, so we're smaller than that. So we're going to go up. Do I see a 0.075? There's a 0.072 right here. 0.072. I'm looking for 0.075. So I'm going to move over this way. Oh, so there, that's the closest number I can find to 0.075. It's 0.0749. Okay, that's good enough for me. And that's in the row that starts with a negative 0.14. And the column, let's shift the book down, is 0.04. Okay, so this entry is the z-score negative 1.44. So don't let that negative scare you, because we're talking about the standard normal distribution. And so here we're just talking about a z that's to the left of the mean. And we knew our mean, or we knew our number was to the left of our mean already. So we should expect a z-score that's a negative number. Okay, so let me shift my book back so it doesn't fall off my desk. And let's go back to my tablet. So the table tells us that our z-score was negative 1.44. So going back here, we'll copy this. I just prematurely did this work. So this tells me my x is 12.05 plus 0.1 times negative 1.44. And so what is that? Oh boy, that's 12.05 minus 0.144, which is going to be 11. What? There's going to be a 6 there. There'll be a 0 there. There'll be a 9 there. Did I do that right? It's just arithmetic. You can fix it later, but that's the x naught. So the probability that our original distribution is less than 11.906 is 0.075. Okay, so this is the number we were looking for. Does that make sense? 11.906. So we're back in this scenario, 12.05, 11.906 is to the left of that. So sure, I mean, it seems okay to me. So how do you do this with R? Okay, that's what you're really asking. How do we do this with R? Well, one of the things we can do with R is we could check our number here. What's the probability that a normal distribution is less than or equal to, or gives us a result that's less than or equal to 11.906 if we know that the mean is 12.05 and the standard deviation is 0.0 or 0.1. All right, so let's see if R gives us the right answer. So pull up R. Probably be good to make that a little bit bigger so you can see it. So I'm going to type in P norm. You said 11.906, 12.05, and standard deviation 0.1. And we hope we're going to get 0.075. Look at that. That makes me happy. Why is it not exactly 0.075? That would have made me really happy, but why am I not surprised that it's different?
Because
The
the
definition of
z-score that we found was for 0.0749, not 0.075.
Right. The value in the Z table we used was not exactly 0.075. It was 0.0749, a little bit smaller. Yeah. So because we made a little bit of an error there, or we introduced a little error there, we expect a little bit of error to be introduced here. Okay.
Dr. Miller,
Yeah.
if we were to kind of add a decimal to that z value that we found, so instead of using negative 1.44, if we did like negative 1.442 or something, like add decimals to try and get a little bit closer, that would make this value closer to 0.075, right?
Yep. Absolutely. So if you tried to be, accuracy begets accuracy. So I'm trying to share this. So you're saying if you were able to carry this out to another decimal place, you're asking, would this be a better approximation of 0.075? Or would this be a better number? And the answer is yeah, absolutely. So there's a good argument for using that interpolation thing I talked about.
Okay.
It would just give you a better number. Now, the table in our textbook, it's like an introductory table of z-scores. You can go out and find tables for z-scores that have many more decimal places in them. Right? You can find whole books where each page is, it's just absurd. It's just crazy. So this is why R is better, because you don't have to mess with those tables. And then I want you to know how to use the tables, because it gives you a sense of this change of variables that's important in statistics. But at the end of the day, verify everything with R. And so I'm here to tell you about another function that you can use in R. And it's not in my notes yet, but I'm going to tell it to you anyway, because I'm taking longer than I thought I would take. It's the function, and I believe I'm sharing my tablet. It's the function qnorm. So qnorm, it takes, let's see, what does it take? It takes a probability, and then it takes a mean and a standard deviation, and it gives you back the x naught. That is, it will tell you what x naught solves this equation. And so let me do this in light blue. So you don't have to, it allows you to circumvent this process of finding a z-score, going to the z table and calculating it that way. So let's see if I'm right. And let's go and look to see if this is the right function. So here's my RStudio. I'm going to type in qnorm. I want the probability 0.075 from a normal distribution that has mean 12.05 and a standard deviation of 0.1. So if I did this correctly, I should get back the number 11.906. So if this is the right function, I should get back the number about 11.906. It'll be a little bit different because 11.906 was a number we arrived at when we introduced a little error from the Z table. So, but let's see what we get. Here we go. Sweet. Okay. So that's how it works. This is a way you can find solutions to questions like this. And these questions are central to the question of finding a confidence interval. So let's turn to that in a second. How much time do I have? I've got 20 minutes. So I would just work with the probability 0.075. And what I was just doing, and I'm sorry my picture is so crappy, is I just found an X naught where this area down here was 0.075. But I want to point out that I also found this, I'm going to call X1 here, where this area was 0.075. So that's a long way of saying I just found a region about the mean that had 85% of the area by symmetry of the normal distribution. Our mean was 12.05. This number down here, I found it was 12.05 minus, what did we say? We said it was minus, no, I don't have it written down. Minus 0.1 times Z naught, and Z naught was negative 1.44. So that's how I'm going to write this down. Right, this down is 0.1 times negative 1.44. And this X1 here is 12.05 plus 0.1. Oh, wait a second. Yeah. Yeah, so this is the way it should work. There should be a plus here. Okay, because this number is less than our mean and this number is bigger than our mean. This pattern works going forward where this would be your mean or maybe your X bar. And oops, this is your standard deviation or maybe your sample standard deviation. So this idea of mean plus or minus standard deviation plus your z-score. These numbers give you your endpoints of an interval. And this interval is what we typically call a confidence interval. So in this example we just did, we could say that we found the 85% confidence interval about mu equals 12.05. That is, so how do you interpret this? The idea here in this confidence interval, and I want you to hear this and understand this because it can't be applied to the main point of this section, okay? The main point of this section has a slight twist to it, but you don't appreciate the twist unless you understand this idea. And the idea is this. If we took 100 different samples of a random variable X, then 85% of them would be in this interval. So when you have a confidence interval, your confidence is in the proportion of, or the probability that a value of your random variable is going to be in that interval, okay? So this is what we mean by a confidence interval, just a generic confidence interval. And the way we construct a confidence interval is this. Is first you choose a value of alpha that's between 0 and 1. This is the way the book talks about it. This is the way statisticians typically talk about it. Then you look at the number that's 100 times 1 minus alpha, and you call that a percentage. And I can't remember if this has a name. But right, this is going to be your confidence. So this alpha here is kind of represents your not confidence. So geometrically, when we're talking about confidence intervals, or the confidence we're talking about is this area. So alpha concerns this. Alpha is the total area of the tails. Okay. So in fact, we'll see in a second that each tail has area alpha over 2 by the symmetry of the normal distribution. Okay, so you choose alpha, you get this confidence, and then, so going back to black here, then you focus your attention on alpha over 2, and then you want to solve what's the probability that your random variable is less than, well, where is the place where your probability is less than or equal to, or your probability of the x being less than the place equals alpha over 2. That is to say, you're looking for this number, x naught. That's the next thing you do. And once you find that number, by the symmetry, by the symmetry of the random normal, you can find the other number x1. Okay, and then your confidence interval is x naught. Ooh, wait a second. Yeah, x naught, x1. And this is why z-scores are kind of nice, because the endpoints of your confidence interval are the mean plus or minus the standard deviation times the z-score. So that's one thing that makes the endpoints nice. If you don't use z-scores, then you have to calculate that distance and then use it to find your other endpoint. So let's do an example. Let's find the 60% confidence interval about mu equals 12.05 if x is distributed as a normal random variable with mu is 12.05 and standard deviation 0.1. Well, and let's, just specify that standard deviation is 0.1. So the variance is 0.01. Okay. So step 1, we need to find that alpha. So 60% is 100 times 1 minus alpha. So that's 0.6 is 1 minus alpha. And so you can subtract 1 from both sides and get negative 0.4 is negative alpha. So alpha is 0.4. And then now, because the normal distribution is symmetric about the mean, we're going to take half of this. Because we're going to have, we're going to have half of our error in the left tail and half of our error in the right tail. So 0.2 will be here and 0.2 will be here. So we want to solve what's the probability that our random variable is what x has a property that the probability our random variable is less than x equals 0.2. So here's where we could go to the z table, or we could go to R. So if we went to R, we'd say Q norm, put in the probability we want, which is 0.2, and then put in our distribution's mean and its standard deviation. So I'm going to do that. You don't need to see me type that because that's all I'm going to type. Q norm of 0.2, 0.05, and 0.1. I get 11.96584. So that's our x naught here. And x1 up here, x1 is going to be mu plus mu minus x naught, right? That's this distance here. So mu minus x naught, that's 12.05 minus what I just computed. So this is, how should I write this down? This is 0.0841621. So add that to my mean, and I get 12.13416212. So these are the endpoints of my confidence interval. The 60% confidence interval is 11.96584 to 12.13416. And I'm just expanding both to the same number of decimal places. You know, really in all practical terms, when you're doing this kind of stuff, probably 2 decimal places is enough. Certainly it's enough for me, especially if you show me your work going up to that point and then showing me how you round. But this is the 60% confidence interval. It means that if I did 100 repetitions of this random variable, I would expect 60 of the outcomes to be in this interval. And the smaller my interval gets, the smaller this confidence gets. Because the smaller the interval is around my mean, the smaller proportion of the outcomes of my random variable are going to end up there. Okay. If I make my interval bigger, well, more of my outcomes are going to be there. If my interval were from minus infinity to infinity, I'd be 100% confident that all my outcomes are going to be there. So there's this inverse proportional, well, there's this proportional, direct proportional relationship or direct relationship between the length of your confidence interval and your level of confidence. So that's something important to keep in mind. So I've got 6 more minutes. So what I want to tell you is this. Let's do another example here. And so this one is really hews close to example 5.1. So let's suppose x is a random variable that's distributed normally with a mean 12.05 and a standard deviation of 0.1. And then suppose x bar is the sample mean distribution that's calculated using n equals 100 samples. Let's find the 95%. So let's find the 95% confidence interval. For some x bar, some particular sample mean. So the thing you need to remember to do this is the sample distribution, the sample mean distribution by the central limit theorem. Okay, and we don't even need to know what X is distributed like, but by the central limit theorem, the sample mean distribution is also normal, and it has the same norm as the underlying distribution. And the variance of the sample mean is the variance of the original function divided by the square root of the sample size. So this is the same thing as the variance is going to be 0.01 over 10. Again, I want that to be variance. No. Yeah, that's what I want. Jeez, that's a small. It's a very small variance. So let's find the 95% confidence interval. So step one is we want to figure out what alpha is. So 100 times 1 minus alpha is supposed to be 95. So that means 1 minus alpha is dividing both sides by 100 is 0.95. And so that tells us alpha is 0.05. And we're interested in alpha over 2. So that's 0.025. So what's the at what number do we have the probability of our sample mean is being less than that number is 0.025. So we can turn to R and we can say plug Q norm of 0.025. Our mean is 12.05 and our standard deviation is the square root of 0.001. So I will share my R with you. Oops. Q norm of the probability to be 0.025. Mean is 12.05. And our standard deviation is the square root of 0.001. All right. And we get 11.98802. So that's the probability that our sample mean is less than 11.98802 is 0.025. So we have our mean is 12.05. Our left endpoint is 11.98, let's say 99. So that means that our right endpoint is 12.05. So this is our confidence interval. Our confidence interval, our 95% confidence interval is 11.99 to 12.05. That's how we find confidence intervals.
Dr. Miller?
Yep.
I don't know if you meant to switch your share, but we're still looking at.
Yeah, thanks, Ashley. I did not mean to switch I did mean to switch my share. So what I wrote down here is I wrote down what R just gave us. R gave us this, and so I wrote down that that's what this means, right? Just plugging in what R gave us for that. And then I wrote down a number line with the left endpoint of our confidence interval and the right endpoint of our confidence interval. I rounded what R gave us. So this is a simple 0.03, that distance. So I know that distance is a simple 0.03, but that becomes our 95% confidence interval.
Professor?
Yes.
If our mean is 12.05.
Yes.
Then it seems odd that our upper end of our confidence
Oh.
interval is also 12.05.
Oh, that's because I screwed up the mean right here, right? So this should be. That's a 0.5, and the.
So
That's
we
what-
get 12.11 then?
Yeah. Yep. So thanks, Patrick, for catching that. So what I want to leave you with, that we're out of time here, and we'll start talking about this next time, is what we've just done is that we've computed these confidence intervals. Okay, where the question mark is something that we get from the confidence level. But actually what happens is that we get an X bar, and when we compute a confidence interval, we report it in this way. And what we really hope is that mu is in the confidence interval about X bar. Because this is the only thing that we can know for certain, right? The sample. And then we can go and compute the confidence interval around that sample. We don't know mu to calculate the confidence interval about it. And what we hope is happening is that the confidence interval around the sample mean intersects with the confidence interval around mu, or rather, the confidence interval around the sample mean contains mu. That's what we're trying to say when we say we have got confidence. And the interpretation for a confidence interval around the sample mean is that if I took 100 different samples of size 100, and in each of those extractions calculated the mean, in this case, 95% of my sample means would fall within this region around mu. So take a look at the text, see how it talks about that subtle difference that I've been trying to allude to. And we'll start talking about that in class on Tuesday. Okay, but that's it for now. Thanks, everybody. Keep on keeping on.
Thanks, Dr. Miller.
Thanks, Ashley. See ya.
Thanks, Dr. Miller. Bye.
See ya, Patrick.